Hello again. This is CS 486 slash 680 Introduction to Machine Learning as taught at the University of Waterloo in fall 2024. This is lecture 17, and today we're going to be talking about advanced optimization methods. So why do we need to think about optimization again? We've been thinking about optimization for this, pretty much this whole course. We've been using a lot of optimization methods. Um, why are we revisiting this now? And so yeah, so we're now four lectures deep into our discussion of neural networks. We've encountered four different types of neural network architectures. So we started off just considering the basic multi-layer perceptron that has, in its simplest form, has a single hidden layer with nonlinear activation functions. So we called this multi-layer perceptron or a feed-forward network, fully connected network. We then also talked about convolutional neural networks that use this idea of sparse connections and weight sharing to be able to do a set of convolutional operations for a specialized task of computer vision and image processing. We then moved on to recurrent neural networks that are best for handling sequential data and transforming, being able to map sequences to one another or sequences to a vector or from a vectors to a sequence. Also some specialized types of recurrent neural networks. This one here, this is the long short-term memory unit, which is pretty popular in the field. And we also talked about the gated recurrent unit, Legendre memory unit, the encoder-decoder architecture when we moved on to language for language translation problems. And then in the last lecture, we moved on to the transformer architecture that enables us to do really fast and parallelizable attention. To be able to selectively attend to different parts of an input sequence and innovate on the architecture or innovate on some of the capabilities of a recurrent neural network without necessarily needing to process data in a sequential fashion. So yeah, while they're wildly different architectures for different specialized for different tasks. The multi-layer was kind of our first approximation of being able to learn features if we don't know precisely what they are. Convolutional neural networks were initially inspired for image data. Recurrent neural networks for sequential data, and then the transformer to be able to deal with sequences without needing to process them one item at a time. So yeah, very very different, but they do share something in common, and that is that they're difficult to optimize. And so yeah, so why am I making that claim? So it comes down to a few different reasons. So the first is that these, we saw that these objectives are non-convex. And so we talked about that in the multi-layer perceptron lecture. So whereas in earlier parts of the course, like our lecture on regression, linear regression, we could count on there being a very simple expression for the loss. And in fact, it turned out that there was a closed form expression for the optimal parameters. In this case, we could actually solve for the weights directly. So we didn't even need to use methods like we didn't even need to iteratively look at the gradient. We could just solve for the optimal weights directly. We did start thinking about non-convex objectives, like when we turned our attention to Gaussian mixture models, and then we had the label switching problem that made the parameters unidentifiable. We got around this by introducing auxiliary distribution and some latent variables that allowed us to use the expectation maximization to alternate between essentially filling in for the missing data or the unobserved data, and then maximizing the likelihood of parameters with those assumed hidden variables. But yeah, now in deep neural networks, there's the loss the objectives are very non-convex, and in general we might expect to see the loss function surface look like have a bit of a egg carton like pattern where there's lots and lots of local minima, um, lots and lots of local minima, and it would be yeah, difficult. There's no we don't really have the techniques um, to get around this, where we really are constrained to using gradient-based methods to start somewhere in the surface, and then arrive at a local minimum. And we've been relying on the idea that you know, even though there are lots of local minima, we've been relying on research that has been telling us that each of these are you know, close in error to the overall global minimum. And so even though we might not arrive at the perfect global minimum, we could get to a local minimum, and that might be good enough for our purposes. So that's been the key assumption that we've been making in this course so far. And yeah, there is research that suggests that the loss function surface might be even less agreeable than that picture in our minds, where there is a global minimum that that is quite a bit better than any of the local minima that we've been encountering along the way. But yeah, in general, the loss function surface is such that gradient-based methods are the only have been the only optimization tool in our toolbox. Another issue with the loss function surfaces is that in general they're ill-conditioned. So whereas we've been kind of counting on you know, being able to estimate a consistent signal or a meaningful signal of the gradient, to be able to follow a smooth learning path from a region of high loss towards a region of low loss here in the center. And so we could tackle this with full batch gradient descent, which would give us a very smooth and predictable estimate for the gradient on our way towards the region of low loss. We also made the argument, or have been using stochastic gradient descent to estimate the gradient using a small batch or mini batch of samples. So yeah, compute the gradient of the loss using a subset of the samples rather than the whole. Rather than the whole batch of samples. And so in a convex situation, yeah, we were relying on the assumption that we would, you know, on average still be able to, on the average over multiple updates, we would still be able to get to the local minimum. And so yeah, this the blue line here, that represents the actual steps taken by stochastic gradient descent. But then the black is averaging over several such steps. And so what we can see is that where even though you know, if we looked at step by step, we might be making a pretty erratic path. Those fluctuations kind of average out in the average out, and we still end up at the local minimum. When the loss function surface is ill-conditioned, though, what happens is that in any one direction in parameter space, the gradient could be quite a bit larger than in some other direction. And then when that happens, we have a difficulty in selecting the learning rate. And so if we were to estimate the gradient at this point, then it would tell us to move primarily in this direction, because this is the direction in which the gradient is changing fastest. But then we would end up at this other side of this valley, And it would tell, and when we get there, it would tell us to take another large step in this direction, and it would cause this zigzagging on our way towards a region, on our way from a region of high loss towards a region of low loss. And so this can make learning inefficient because we're not making smooth progress towards the region of low loss. We're spending a lot of our time zigzagging back and forth across this across this valley in the lost surface landscape. And then last but not least, the just physically writing out the gradients themselves has become a bit of a challenge. So yeah, whereas before in earlier parts of the course, the expressions for the gradient of the loss with respect to the parameters, we've been able to make these for very simple expressions for those gradients. So this is the case of the in simple linear regression or least squares regression. Things got quite a bit more complicated, especially with recurrent neural networks, where we had to do things like keep track of the indirect contribution and the direct contribution of the gradients with respect to the recurrent weights or the weights between the hidden units, and keep track of how those weights appeared repeatedly throughout the unrolled view, essentially to do back propagation through time. And yeah, if you notice, we didn't even bother trying to compute an expression for the gradient of the loss with respect to some parameter in a transformer. And there's also now, especially with GPT-4, we're talking about literally trillions of parameters. And so yeah, we didn't even bother talking about what the gradient of the loss would be through a multi-head self-attention block. And so yeah, there's a couple challenges here. It's getting challenging to just write out the gradients and make sure that the code reflects the analysis that we did by hand. But then also, we're starting to deal with models that have trillions of parameters. And so being able to compute gradients is also going to be, more tedious and then also more prone to error. So yeah, hopefully at this point, yeah, you've got a sense of at least the unique challenges or the more extreme challenges for, doing optimization in a deep neural network. And so today we're going to talk about methods to do optimization in deep neural networks a little bit better. And so this talk is, this lecture is roughly structured in a way along three key phases. So the first is we're going to think about how we can start things off the right way. How we can initialize the parameters to be able to use gradient descent based methods a little bit more effectively. So yeah, we know that the loss function surface is non-convex, so we have to start somewhere. And yeah, so yeah, where can we start? Can we start things off a little bit better to be able to make the optimization process go a little bit more smoothly? So that's the first part of the talk. And then the second part of the talk is about, okay, once we've figured out where to start, how to initialize our parameters, are there considerations to navigate the loss landscape more effectively? Can we move over it faster to converge to a local minimum in less time with fewer updates? And then finally, I'm going to link we're going to think about how to just compute those gradients more reliably to make that process less error prone and less tedious for us, especially as we scale up to really large networks like transformers. So in this last part of the talk, I'm not gonna cover it as part of this video. I'm just going to set it up and then link a Jupyter notebook in the comments. But yeah, here in this last part, we're going to be talking about automatic differentiation or autograd features that are built into most deep learning libraries. All right, so on to the first question. What are some parameter initialization strategies for these uh, gradient descent based methods? How can we start things off to end up somewhere better or somewhere better in the loss function landscape? Um, so yeah, the non-convexity of the loss function surface of neural networks. This means that the initial parameters that we select, it influences the minimum to which we converge, if we converge at all. And so I'd love to be able to say that, um, that there might be some way to know beforehand how we can select those initial parameters to be able to end up at some global minimum. But we actually don't have that theoretical insight right now. There's actually very little theoretical guidance on how to go about selecting those initial parameters. Um, One thing we know with absolute certainty, though, is that the parameters must be initialized in such a way to break symmetry. Um, so, for example, let's consider a simple neural network with one input, one output, and two units in the hidden layer. And then to keep things simple, we'll assume these neurons are linear. So the activations of these hidden units are simply a scaled version of the input x. So W1x and then W2x. So these activations H1 and H2, they're the activations of the units in this hidden layer. And then yeah, to also keep things simple, let's assume that the output is just a weighted sum of activities in the hidden layer. So there's no bias, no nonlinearity on the output either. Yeah, and then so totally, this is just a weighted sum of the units in the input, weighted sum of the input. And so if we initialize both hidden units to have identical weights, they're going to produce the exact same outputs given the same inputs. So yeah, let's say we initialize, or let's say we set the weights for both hidden units in the first layer to some constant value. So W1 and W2 is some scalar A. And then initialize the weights on the output connections to the same value as well. So V1 and V2 are some B. And yeah, what this means is that during the forward pass, both of these hidden units, they're going to compute the same value because W1 is B and then W2 is B. So this is just going to be H1 is going to be BX, or sorry, W1 is A and W2 is A. So H2 is just going to be AX and H1 is going to be AX as well. So yeah, during the forward pass, these two units are going to compute the same value. They receive identical weights and they're getting the same input. And so then if we when we compute the gradient during backpropagation, what we're going to find is that both units are going to receive the same gradient value. And so their updates are going to be identical. So the gradient of y with respect to W1. So there we're interested in this output here. So with respect to W1, this term is just a constant, and then the gradient is going to be V1x. So that's going to give us that there, and that's going to be Bx. And then the same thing if we try to compute the gradient of the loss with gradient of the output with respect to W2, that's just going to be V2x, which is going to give us Bx, so the same argument. And so this symmetry is going to persist at every single update. And it's going to reduce this hidden layer to behave as though it only had a single unit, really. And so this is going to put, yeah, we're not going to get any more expressive capacity than if we had simply had a single hidden unit in this hidden layer. So yeah, this is not at all what we want. And even if we had nonlinearities on on the hidden unit or the output, the same argument would apply. We're still computing the exact same gradients with respect to these parameters. And so, yeah, one way to avoid this the symmetry problem, or that yeah, a way around this symmetry problem that practitioners figured out early on, is to initialize the weights randomly to draw them from some distribution. But then we have a new problem, because there's how can we, what scale of distribution, where, what should be the parameters of that distribution. Um, and we know that the scale of the weights can have multiple effects on the behavior of the network. So for example, small weights, for example, they can help avoid issues like exploding gradients, chaotic behavior in recurrent neural networks, saturation of activation functions for certain kinds, like the sigmoid or the tanh. And these problems, especially the chaos and the saturation, they can arise because large initial weights can cause the values passed through each layer to grow exponentially, which would destabilize both the forward and backward passes. On the other hand, we might want large weights to be able to have a strong symmetry breaking effect, and then also to avoid the vanishing gradient problem. And so, yeah, with vanishing gradients, that happens with very small weights. Signals can become too weak as they propagate through each layer, especially in deep networks. And so this can cause gradients to diminish to nearly zero, to make it difficult, making it difficult for the network to actually update the parameters effectively. And so the result might be that each unit behaves similarly, even though we've taken care to actually break the symmetry. And so this suggests the fact that there's reasons to favor both small and large weights. It suggests that there could be an optimal point to trade off between these two and choose weights that are, large enough to propagate information effectively without causing instability. And so in a 1986 paper that popularized backpropagation by Rummel, Hart, Hinton, and Williams, they indicated to start with small random weights. And for quite a long time, this was kind of the best guidance, the most precise guidance that the community had. It wasn't super clear what small meant, or what random meant, like how small was too small, from what distribution. Yeah, these details weren't made. Yeah, it wasn't abundantly clear what was meant, or how they managed to train their networks exactly. And so one heuristic to try to pin down what that distribution should be came from focusing not on performance directly, but instead on trying to preserve the activation levels as well as the gradients at each layer in the network. So the idea is that if we can keep the variance of the activations and the gradients roughly constant across the layers, we can avoid problems like exploding or vanishing gradients, which are in turn obstacles for training deep networks. So what do I mean by this? So let's start with the output of a single linear neuron in a fully connected layer. So for neuron I without any nonlinear activation, its output, its activation is that's a weighted sum of the inputs xj. So the input features are indexed x1, xj through n sub n, x sub n in. So xn is the number of inputs to this neuron here. And if we assume that each weight wij is drawn from a distribution with zero mean and some variance, and that the inputs also have zero mean and some and a given variance and are independent of each other in the weights. Then the expected value of the output of the ith neuron, its mean, that's zero. The variance, on the other hand, that's going to reduce to the product of the number of inputs, the variance of the weights, sigma squared, and then the variance of the inputs is gamma squared. Um, and so to prevent the variance from growing or shrinking as we propagate forward, we would want to set this product to one, as this would mean that the variance remains stable. We would face a similar challenge with the gradients, though. Where we want to prevent the gradient variance from exploding or variance. But then in that case, the quantity of interest would be the number of outputs. So that would be the number of outputs from a given layer, from a given neuron. So that'd be the kind of the fan out. And so we can't satisfy both of these constraints simultaneously, but we can split the difference. And so let's just say that the average of these two should be equal to one. And what this by rearranging, we can solve for the variance to be able to satisfy these two conditions simultaneously. That's going to reduce to so if we want both of these to equal to one, then we can then the variance is going to be the square root of 2 over the sum of the number of inputs and the number of outputs. And so if we draw from the variance of if we draw the weights from a distribution with a variance with this variance, this is known as the Xavier initialization. So the initialization known as the Xavier initialization, it sets the variance of the weights to 2 over the sum of the number of inputs and the number of outputs. And so this represents a compromise between maintaining stable activation and gradient variances. And so for a Gaussian distribution, we can draw the weights from a Gaussian distribution by using this variance condition directly. But we could also draw weights from a uniform distribution, because the variance of a uniform distribution from minus a to a is a squared divided by 3. And so if we plug that in to a uniform distribution, we could sample weights from a uniform distribution instead with this strange factor of 6. But that's where it comes from. And yeah, so this choice of initialization scale, that's what we call the Xavier initialization. It was proposed by Gloro and Bengio in 2010. It's become a practical standard for weight initialization in deep networks, and it helps maintain a balanced flow of information both forward and backward through the layers. And so this is critical for efficient training. And it aims to avoid the extremes of vanishing and exploding gradients to try to make it easier for networks to learn effectively across many layers. Empirical results demonstrate that the initialization heuristic based on the number of inputs and outputs of a given layer does indeed help to maintain the scale of activations as well as backpropagated gradients. And so these figures here, they show histograms that compare how activation values on the left and then backpropagated gradients on the right are distributed across layers when Xavier initialization is applied, as opposed to standard initialization. And so on the left-hand side, we see that the distributions of activation values across 5 layers using some activation function. And so in the top left figure, this is a standard initialization. So the peak of the distribution increases as we in deeper layers. So yeah, so what we see, yeah, layer one in red, layer two in green, layer three in blue, four, and then five. And so what we see is that we start off with a very wide variance of activations, but this becomes increasingly concentrated around zero as we get deeper in the network. And so what this means is that signal is being lost as it propagates through the network, as it propagates forward through the network. Um, and but then in contrast, with the Xavier initialization, this results in a consistent distribution across distribution of activations across layers. So now each of these are on the same scale. So yeah, each layer has a pretty stable spread. And then the opposite goes for the distributions of backpropagated gradients across layers. And so with a standard initialization, um, gradients would diminish when the error must be back propagated to the earlier layers in red, compared to the deeper layers in blue. So yeah, and this is what we're seeing here is the vanishing gradient problem because yeah, at the output we have a very wide distribution of gradients. So there are some large gradients as well as some very yeah there's large negative gradients and large positive gradients. Um, Not too many around zero, but then as we back propagate these gradients towards from the output back to the input, then these gradients get more concentrated around zero. So they're getting smaller and smaller, smaller and smaller on the whole. With the Xavier initialization, the back propagated gradients maintain a consistent scale across layers. Um, yeah, this helps ensure the conditions that often lead to a meaningful update during training. That being said, though, Xavier initialization doesn't directly improve performance. It instead optimizes the flow of information through the network. And this is thought to make it easier to train deeper networks effectively by preserving the scale of activations and gradients across the layers. So it's an indirect way to improve optimization. Um, yeah, Xavier initialization isn't the only game in town. It's one of many initialization strategies. There are many others. I'd like to mention a couple that focus on different characteristics of the parameters than just the scale of the distribution from which they were drawn. So for example, some initialization methods, they involve setting the weights as random orthogonal matrices. This is often paired with a carefully chosen scaling factor or gain to account for the nonlinearity applied at each layer. And yeah, so this approach is based on viewing a deep network as a series of matrix multiplications where each chosen gain factor ensures that the activations and the gradients maintain a stable norm as they propagate through the network. But the idea is that by setting the gain correctly for different activation functions, you could train networks with that are very, very deep, sometimes as much as 1,000 layers. Another alternative is sparse initialization. And so this avoids individual weights being initialized to very small values when the layers are very wide, by limiting each neuron to have limiting each neuron to have only a few non-zero weights initially. And so this method keeps the overall input to each neuron consistent regardless of the number of total inputs. And so sparse initialization can promote diversity among neurons at the beginning of training. This can be beneficial for avoiding redundancies and encouraging unique representations in each layer. But it doesn't impose a strong prior on the weights or a strong bias, because some weights are going to start with large initial values. And so yeah, this can cause issues where those strong initial values can be slow to adjust through gradient descent. So yeah, each of these three strategies, they address some specific initialization challenges to try to maintain the signal flow to promote diversity or managing the parameter scale. Sparse initialization, especially, is useful for the case of very wide layers, and so the architecture and depth should be taken into account for initializing the parameters. So we talked about some initialization strategies for the weights, and while that got a bit complicated, the biases are much simpler. Typically, biases for hidden units are just initialized to 0, and this approach works well because biases mainly serve as an offset to the weighted sum of inputs in the neuron, and so setting them to 0 doesn't usually interfere with the network's ability to learn different feature representations. For biases on the output, though, sometimes we might want to take a more targeted approach. So you might want the network to better reflect the marginal statistics of the training data. And so you could use the biases to approximate those statistics. So for example, in a classification problem with an imbalanced data set, where one class is much more common than others, you might want to initialize the bias to account for that imbalance. And so the idea is that to set the bias initially, that the output distribution is similar to the distribution of labels in the data set. And so you could ensure that the network starts with a bias towards the majority class on the output. Okay, so that was all about setting the initial parameters for the network, yeah, it was primarily around symmetry breaking, but then also selecting the weights to avoid the exploding and the vanishing gradient problem. So that's about the most theory that at least we're going to get into in terms of parameter initialization. But yeah, we figured out how to start things off, and now we need to traverse the loss landscape in order to find at least a local minimum, or ideally a global minimum. And so, are there ways to traverse that loss landscape more efficiently to make use of the local gradients that we know we're going to need? And so one thing I said earlier was that ill-conditioned loss landscapes, they can be challenging for these steepest descent algorithms like gradient descent and stochastic gradient descent. So as a quick recap, we update the parameter theta in the direction opposite that of the gradient. So that is the parameters at time step t. They're those at the previous time step, less some fraction of the gradient at that point, where eta is the step size in the direction opposite that of the gradient. And so in the context of stochastic gradient descent, we don't calculate the gradient over the entire data set, but rather over a mini batch of m samples. And so this approach could add some noise in the gradient estimates, which could be beneficial in avoiding local minima, but could also lead to challenges in convergence. But yeah, the figure on the right here that illustrates how gradient descent behaves on a loss landscape that is ill-conditioned. So these contours represent regions of identical loss. And so these dark colors, they represent low loss, whereas these yellower colors represent high loss. And so if we use a small step size, so for example 0.1, we're making a relatively smooth convergence as the algorithm moves down this valley towards the minimum. But then, because the step size is small, the progress is going to be pretty slow. So it's going to take us a long time to actually get there. And so the path shows, gradual descent along the valley, but it's going to take us many, many steps to actually approach this minimum. On the other hand, if we try to use a larger step size to try to speed this up, the algorithm is going to make initially, fast progress. So if we've got the same starting point, but then we're going to make a huge step all the way over here. So that's great. That's getting us quite a bit closer to the minimum. But then when we get there, we're going to start to make some erratic steps that aren't directly aren't very focused on getting us closer to this minimum. Um, so yeah, we're going to start to exhibit some overshooting behavior where we're actually just toggling back and forth along the walls of this valley. So we're just zigzagging across the valley. We're not actually getting to this local minimum. And so this is a consequence of the step size being, large enough that the updates are overshooting. Um, and so if while the larger step size caused initially fast progress, the erratic movement, this slows down the overall convergence as the path isn't directed towards this minimum. So yeah, this is a fundamental challenge in gradient descent or these steepest descent-based methods, because we need to select this step size eta. Small step sizes can be stable but slow, and then large step sizes can accelerate progress, but they're going to introduce this instability. And this is a particular challenge in these ill-conditioned lost landscapes. And so the difficulty in tuning the learning rate was the motivation behind incorporating this concept, a concept of momentum. Um, and this is going to result in the size of the update changing based on the previous history of updates. Specifically, if we let g of t minus 1 be the gradient at the previous time step, um, then the parameters theta are updated not by the gradient directly, but instead by this velocity term v. And so this velocity term, in turn, this is a linear combination of the actual gradient observed and its own previous values, the previous value of the velocity. And then alpha and epsilon, these are going to be hyperparameters. And so this recurrence, this means that we now have a kind of memory in the optimization process. So the algorithm is going to tend to move in the direction that it has tended to move in the past. Just like we would expect of the physical property of momentum. And then the overall weight update, delta theta t, this is influenced by both the current gradient and the accumulated velocity. So yeah, current gradient scaled by epsilon and the accumulated velocity alpha t scaled by alpha. And so this results in many advantages. So the figure on the right here, this depicts the contours of the loss function for a two-dimensional parameter space. And so yeah, these are contours, regions of high loss here outside, and then regions of low loss here in the center. And so these black arrows, these are the gradients that are observed at a few points along a learning path with the momentum update. And so what we see is that, starting from a region of high loss and progressing towards the local minimum, the largest component of the gradient is in the direction, tends to be in the direction orthogonal to the direction of the local minimum. And so with stochastic gradient descent, this would cause the learning path to just zigzag on its way towards the minimum if it ended up making progress there at all. The learning path using the momentum update, though, that's shown in red. And so because velocity depends on the observed gradients in the past, momentum helps to reduce the inefficient zigzagging behavior that we would see in gradient descent, because those large fluctuations are going to cancel each other out over time. But the small progress that we're making towards the center, that's going to be preserved. And so, yeah, what we would see is that the large fluctuations back and forth, they're going to cancel each other out. And so the zigzagging is going to get smaller and smaller as we get to the center. And then on the other hand, if we are making, small, steady progress, the velocities are going to accumulate and will accelerate towards the minimum. That's not yeah. So that's probably shown here as we can see that the direction in the gradients in the direction of the minimum are tilting towards the minimum on each step. So yeah, the velocities are going to accumulate as we accelerate towards the minimum, and so this can help the optimizer overcome flat regions that might appear in the landscape. Why is it called momentum? And so it comes from the fact that the velocity term v can be understood as the momentum of a unit mass particle that's moving through the lost landscape. And then where alpha's between 0 and 1. This controls how much past gradients influence the current update. To get some stronger intuition for how momentum works, we can analyze the velocity updates. And so the equation for velocity at time step t, we know that it depends not only on the current gradient, but also on a fraction of the previous velocity. And so if we apply this equation recursively, so substitute this in first for 2 time steps back in the past, and then 3 time steps back in the past. Because alpha is less than 1, greater than 0, this means that the gradients observed at the most recent time step, they're going to have the largest contribution, whereas those further back in time, like 2 time steps back, 3 time steps back, they're gonna have a weaker contribution. And so, in other words, this recursive dependence means that gradients from earlier steps are still going to have an influence, but they're going to decay over time. And the strength of that decay depends on our choice of alpha. So the figure on the right here illustrates how different values of alpha affect the weighting of past gradients for typical choices of 0.5, 0.9, and 0.99. When alpha is close to 1, the influence of previous gradients is going to persist over a long period. So this is going to give a lot of memory to the optimization process. On the other hand, decreasing alpha is going to cause those contributions for contributions of gradients far off in the past to be weaker on the current parameter update. Some special cases for alpha also provide some insight into the behavior of momentum. So for example, when alpha is 0, the momentum is not going to have any memory, and the update reduces to standard gradient descent. Conversely, if the gradients are identical across all time steps, so yeah, all previously observed gradients are some gradient g for all t. The cumulative effect of momentum is going to allow for a much larger step proportional to the sum of gradients divided by 1 minus alpha. And so this feature of momentum makes it especially beneficial when the gradients are aligned. So it's going to amplify the step size and is going to accelerate the convergence in those cases. And so, yeah, the idea is by dynamically balancing the influence of past gradients, momentum tries to optimize the trade-off between stability and convergence speed. So it makes it a powerful tool for navigating complex optimization landscapes. So momentum alleviates the sensitivity to wildly different costs in different directions, but it does so at the expense of introducing another hyperparameter. And so to sidestep this, AdaGrad was introduced. And the core idea here is actually to update, to adjust each parameter's learning rate according to its own history of gradient updates. And so why do we want something like that? So this property of a separate learning rate parameter, learning rate per parameter is desirable in neural networks with multiple layers, for example. Yeah, specifically in early layers of a network, gradients might tend to be very small, especially if we don't have the Caloro initialization. And this would cause cause small updates even though they were important. Um, and then additionally, different layers can have different gradients due to fan-in differences. So for example, units in the layer at the top here, they've got 4 inputs, whereas units in the layer on the bottom, they've got 3 inputs. And so this would tend to change the magnitude of activations and therefore the gradients. So yeah, assigning a single learning rate across all parameters in this whole network could lead to some undesirable effects. AdaGrad addresses this by automatically scaling the learning rate individually for each weight. So specifically, in AdaGrad, the update rule for the JAFE parameter at time step t then involves dividing the gradient of that parameter by the square root of this sum of st and epsilon. And so this epsilon is just a small constant to avoid numerical stability issues associated with division by 0. But st, this is the square root of the sum of past squared gradients. And so all past squared gradients. And so this means that the term in the denominator is going to grow as training progresses. And so if a parameter has large gradients consistently, the denominator is going to grow quickly. And so the effective learning rate for that parameter is going to decrease. And so this helps the optimizer be sensitive to infrequent or small but important updates. So it's going to amplify changes for parameters that change infrequently and dampen updates for frequently changing parameters. AdaGrad was specifically designed to enable rapid convergence in convex settings, and it performs well, because it can converge rapidly towards a minimum by focusing on parameters with the most significant contributions to the loss. A downside, though, is that the denominator could grow too fast. This denominator could grow too fast, and the effective learning rate can decay too quickly. And so this means that AdaGrad could effectively run out of steam if it has to traverse a flatter region in the loss surface, like something like this on its way towards a global minimum. And so this can slow down convergence before reaching the global minimum. Despite this, though, AdaGrad's adaptive learning rate has made it a powerful tool, particularly for sparse data applications like natural language processing, where certain features like rare words appear infrequently and require higher updates, higher learning rates when those updates need to occur. RMS prop is an optimizer that modifies AdaGrad to perform better in non-convex settings like those encountered in training deep neural networks. And so the high-level update equation of RMS prop, it has the same structure as AdaGrad, but in RMS prop, the denominator S sub t, it's calculated as an exponentially weighted moving average of past squared gradients. So past squared gradients, and then it's controlled where the memory is controlled by this parameter beta. And so the weighted average tries to achieve the best of both worlds by smoothing out the effect of gradients over time, but without letting really old gradients dominate. And so this is particularly helpful when navigating non-convex landscapes. And so in other words, the learning, the really the fast learning rate decay issues of Adagrad are alleviated in RMS prop by essentially combining it with the approach taken in momentum, where we had that exponentially weighted average of observed gradients. The reason why it's called RMS prop is because beta is usually set to 0.9. And so this makes the denominator, in this case, makes the denominator approximately equal to the root mean square of the previous gradients observed. While eta grad accumulates the sum of squared gradients over time, leading to an ever increasing denominator that can make the learning rate shrink excessively. RMS prop discards extreme past gradient information by using an exponentially weighted moving average instead. And so this way, RMS prop only considers recent gradients to allow the learning rate to adjust dynamically without decaying it too quickly. And so in a non-convex surface like the one shown here, the learning path might need to pass through different structures before it arrives at a region that behaves like a convex bowl near the minimum, near the global minimum. And so by this point, Adagrad might have come to all but a halt over a flat landscape in the lost surface before it could find a convex bowl like that shown here. RMS prop though, it would maintain a steadier pace. And so this makes it more resilient when passing through regions with different curvature. It means that it can kind of reset its effective learning rate as it approaches a local convex bowl, as if it were an instance of Adagrad initialized right at this point. Key takeaway, by discarding older gradient information, RMS prop ensures that the learning rate doesn't become too small too soon, allowing for quicker convergence once it reaches a bowl-like structure. One final comment is that RMS prop lacks a guaranteed convergence to the minimum because it has this adaptive learning rate that doesn't necessarily decrease over time. But it still is a popular choice in practice, especially for training deep neural networks, because it strikes a good balance between stability and adaptability in complex landscapes. All right, so to get a sense of how these different optimizers compare, this animation depicts the learning paths followed by different optimizers in a non-convex loss function. And so each of these points represents one optimizer, where the red is stochastic gradient descent, green is momentum, blue is Adagrad, and black is RMS prop. There's also two others, NAG, which stands for Nesterov accelerated gradient in purple, and Eta delta in yellow, which we didn't talk about today and are outside the scope of this course. The surface itself is shaped like a saddle, so it's concave along one axis and then convex along another. So off the top, we can see that SGD, stochastic gradient descent, is making pretty slow progress. So it's barely moved at all by the time the animation's finished. Adagrad and RMS prop, they're the clear front runners from early on. They've pulled way ahead almost immediately. Momentum oscillates back and forth for a bit before eventually gaining speed to catch up with the others. So starting with stochastic gradient descent, we see that it's very slow and struggles to make significant progress. So without adaptive scaling or momentum, it just follows a straightforward, consistent path, but is slow. Momentum-based optimizers like momentum, it accumulates the gradient direction over time. And so it helps it gain speed in the optimization direction. But because of the inertia from accumulated gradients, momentum tends to overshoot when transitioning through different slopes. And so it's going to exhibit oscillations. And so this might be confusing because we said it was going to help with oscillations, but we didn't say it was going to get rid of them completely. And so this oscillatory behavior stems from momentum's tendency to carry forward with velocity. So it behaves like could behave like an underdamped system where the friction or damping parameter influences how fast it settles. Adaptive optimizers like AdaGrad and RMSProp, they adjust the step sizes based on the gradient information. And so for parameters with consistently large gradients, for example, in this direction, these optimizers, AdaGrad and RMSProp, they're going to reduce the effective learning rate. So it's going to enable smaller controlled steps in those directions where while allowing larger steps in the flatter regions. In another example, this time this is the Beal function. The same colors. So stochastic gradient descent is in red, momentum is in green, AdaGrad in blue, and RMSProp in black. So due to the initial large gradient, momentum shoots off and bounces around. AdaGrad almost becomes unstable for the same reason, but is caught just beforehand. Algorithms that scale the step sizes like RMSProp, it proceeds a little bit more like accelerated stochastic gradient descent. So it doesn't become unstable, but proceeds a little bit more like accelerated gradient descent on its way towards the minimum here. While all of these optimizers are still in use by practitioners today, by far the most popular one is called ADAM, and that stands for adaptive moment estimation. And so it uses the gradient to maintain an estimate of both the momentum, the first moment, and its variance, the second moment. And so in the ADAM algorithm, there's two terms that are calculated to estimate the moment and the second moment of the gradient. So the momentum term, m sub t, that's an exponentially weighted average, moving average of the gradients, controlled by parameter beta 1. And then similarly, ST is the second moment, so it's a measure of the gradient's variance, and that's its evolution is controlled by parameter hyperparameter beta 2. Beta 1 and beta 2 are typically set close to 1, but beta 2 is usually larger than beta 1, and so this second moment is going to move more slowly compared to the first moment. So the slow adjustment helps to stabilize the optimization process, particularly when there's high variance in the gradients. Since M sub t and S sub t are usually initialized at 0, there's an initial bias in these estimates towards smaller values, especially in the early stages of training. And so to correct for this bias, Adam applies a bias correction term, denoted as M hat T and S hat T. And these adjust for the early underestimation of the moments. And so then Adam computes the parameter update delta theta T by scaling the bias corrected momentum term by the square root of the bias corrected second moment plus a small epsilon. And so this scaling, similar to RMSProp, helps prevent the issues when the gradients have high variance to enable smoother and more effective, more efficient convergence. Adam's approach is unique because it combines the benefits of both momentum and adaptive learning rates, which makes it effective optimizer in many machine learning applications, especially deep learning. The theoretical properties that might explain Adam's success in practice are still under investigation to the best of my knowledge. And yeah, we won't be getting into that, at least in this course. But some intuitions can be gained in low dimensional settings. So this animation depicts the behavior of different optimization algorithms in a non-convex function with two local minima. So the plot shows the paths taken by each optimizer starting from the same initial point as they converge to one minima or another. So the colored dots represent different optimizers. So cyan for standard gradient descent, momentum in magenta, eta grad in white, RMS prop in green, and then atom in blue. So in this example, we can see that yeah, Atom combines momentum and the adaptive learning rates, and it quickly adapts its step sizes and moves towards the global minimum pretty quickly over standard gradient descent or momentum alone. Eta grad in white also adapts its step sizes based on past gradient, but tends to slow down significantly over time. And then RMS prop yeah, improves on eta grad by maintaining a moving average of squared gradients, which prevents the drastic reduction in speed, drastic reduction in learning rate. Eta grad, RMS prop, and Atom are adaptive optimizers. So this means that they adjust their learning rates based on the magnitude of past gradients for each parameter. And so this adjustment allows them to take smaller steps in regions with high gradient variance and larger steps in flatter regions. And so this adaptivity means that they're more likely to skip over local minima and saddle points along the way towards a global minimum, unlike SGD and momentum. Atom also incorporates that bias correction, which helps it manage the initial steps more effectively. So it stabilizes earlier and it focuses on a clear direction. It's important to note that yeah, while these visualizations might be useful for building intuition, they are limited by the low dimensionality of the parameter space. We are considering the behavior of these optimizers in a very low dimensional setting, and this isn't we shouldn't trust these intuitions for I guess a deep learning setting. Specifically because deep learning models operate in an extremely high dimensional spaces with, potentially millions or billions or trillions of parameters, where the dynamics of optimization can be very different. So despite the seeming simplicity of stochastic gradient descent, it continues to be used in those high dimensional contexts. In these high dimensional contexts. But Atom is popular partly because of it. It has been found to have reduced sensitivity to its hyperparameters beta 1 and beta 2. But the practical performance of these algorithms in high dimensional spaces is still an active area of research. All right, so to summarize quickly before we move on, we encountered, we saw four new optimizers today. Stochastic gradient descent with momentum, eta grad, RMS prop, and Atom. Momentum has the momentum parameter alpha. Typical choices for that are 0.5, 0.9, and 0.99. There was also that learning rate epsilon. From the point of eta grad onward, the learning rate, I switched that to eta. So eta grad has a global learning rate, and then it's also got a constant for numerical stability, epsilon. RMS prop also has a global learning rate. It's also got the decay rate beta, and it's also got a constant for numerical stability. And then last but not least, Atom has a global learning rate, two decay rates, beta 1 and beta 2. Typically, beta 1 is larger than beta 1 to allow the variance estimate to evolve more slowly than the mean, the gradient mean estimate. And it also has a constant for numerical stability, epsilon. All right, so we talked about how to traverse the lost landscape using more efficiently using these optimizers. But now the last problem that we wanted to tackle was how to compute the gradients more reliably, because it's these networks are getting more complicated, and it's getting more difficult to compute those gradients by hand, to analyze them. And therefore to train the networks. Yeah. So how can we compute the gradients more reliably? And so yeah, the answer is we're not going to do this anymore. So modern deep learning libraries, they've got built-in methods for automatic differentiation to handle that for us. And so I'm gonna link in the comments section a Jupyter notebook that pulls together a few PyTorch tutorials to show how this is done. The feature is usually called AutoGrad, standing for automatic differentiation. And so what this does is going to automatically compute the gradients with respect to some function for us, some objective that we've defined, given a particular neural network architecture. As a small aside, I would love to point you to this video from Jan LeCun that he gave at a workshop at NeurIPS in 2007. Yeah, that was a long time ago, almost 17 years ago now. And at the time, deep learning was not hadn't really been explored at the time. It was a bit more, it was more niche, certainly. It wasn't as mainstream as it is today. We had very few deep learning libraries. It wasn't something that anyone could do. And so at around the 30-minute mark in this video, he starts to talk about how within the field of AI or machine learning, people were having issues reproducing his results. And he starts to talk about how there is one individual down in California, this guy that he can reproduce my results, so it's not my fault. It's something's wrong with the field. And he goes on to advocate for the need to use automatic differentiation, and how this has been a technique that he's been using for decades, and urging the field to adopt it. And so it's remarkable that now we've come all this way, and we now have these tools that are very easy to use in these deep learning libraries. So yeah, take a few minutes, follow the link in the comments, and play around with the Jupyter notebook. Okay, so hopefully you've taken a few minutes to look at that Jupyter notebook, play around, understand automatic differentiation. All right, and we'll do a quick summary. So yeah, what do we talk about? So we talked about the need for symmetry breaking in a neural network to start things off, such that we can actually cause a network to behave as though it has multiple units in the hidden layer. We talked about three initialization strategies. So this was the drawing weights from a random distribution according to the number of inputs and outputs for a particular layer, orthogonal initialization, and then sparse initialization. We then also talked about the when you would want to use one of these initialization strategies over the other based on the architecture considerations like the width of a given layer or an extremely deep layer. Um, we also talked about yeah, spent quite a bit of time on momentum or adaptive learning rate based optimization algorithms. Compared the performance to stochastic gradient descent and the extent to which the loss landscape is ill conditioned. We presented the gradient update equations for four of these: momentum, eta grad, RMS prop, and atom. And then we talked about the strengths and limitations of the different optimizers. And then hopefully if you hopped over to take a look at that Jupyter notebook, you'll be in a good position to use the auto differentiation or the autograd tools, at least in the PyTorch library. All right, so that brings us to the end of this lecture today. I hope you got a lot out of it, and we'll see you back here again next time, where we're going to turn our focus to deep generative models, starting off with variational autoencoders as well as normalizing flows. All right, we'll see you back here then.